To architect a custom UI view that is triggered from a single point, but expands far beyond its initial layout boundaries, we have to rethink how mobile rendering engines handle space. Look at this wireframe. When a user clicks this standard mobile trigger button, it immediately bursts into a screen-spanning radial array of circular targets. This visual fluidity requires a backend capable of masking high-frequency state changes and significant coordinate complexity. Beneath that smooth motion lies a managed framework of discrete state transitions and absolute coordinate geometry. The core tension of building a component like this is execution. You have to force a screen-covering layout transformation without collapsing the main rendering thread or violating the restrictive bounding box of the parent container. The architecture relies on three specific pillars: view hierarchy decoupling, parallel coordinate tracking, and parametric kinematic interpolation. The separation of these three functions is the technical foundation for high-performance, dynamic spatial views. We start with a limitation native to standard mobile development. Views are strictly bounded by the dimensional constraints of their parent layouts. A button cannot draw pixels outside its assigned container. The ensure overlay attached subroutine manages the handoff from the local layout to the global canvas, allowing us to bypass this constraint. Instead of trying to force the trigger button to expand outward, the component detaches its primary rendering canvas from the standard document flow entirely. To escape its nested bounding box, the component injects an absolute layout, P&L overlay, snapping over the root structure. On top, P&L backdrop handles screen dimming and touch interception. Next, P&L piece layer houses the condensed placeholder buttons. Finally, P&L button layer forms the highest interactive destination layer. During this injection phase, layout parameters natively passed as raw integers must be explicitly scaled using device-independent pixels, or DIPs. This explicit scaling ensures the geometry maintains its structural integrity across varying display densities. Escaping the localized bounding box through this absolute overlay injection is the absolute prerequisite. Until the canvas is detached, no spatial animation can occur. With the canvas established, we need a centralized data structure. Expanding an array of targets requires managing the independent states and physical references for every single button simultaneously. This node tree representation shows how the LST button records list manages these states. It stores a localized map object for each button, containing its payload, text, icons, and visibility. Crucially, the map holds two specific memory references, one linking to a piece view and one to a button view. Those two references represent the bifurcated geometry of the system. We'll start with the first geometric state, the pieces. This top-down 2D schematic shows the trigger button. Inside, pieces are mathematically arranged into condensed placeholder patterns, like this 3x3 grid known as .91. This dense layout uses specific horizontal and vertical margin parameters, keeping it confined within the trigger's dimensions. The buttons serve as the secondary geometric state. These are the fully extended interactive UI targets. As we zoom the schematic out, we fade in the wide SC91 circular layout. This represents the final resting position of those targets. Now we draw explicit vector lines connecting the center coordinate of each condensed piece to the exact center coordinate of its corresponding expanded button. These vector lines represent the exact mathematical delta that the animation engine must calculate and process before a single pixel is ever rendered on screen. The component achieves this organic growth by mapping two strictly defined topological states. Processing that mathematical delta falls to the animate boom routine. The core challenge here is moving the UI elements fluidly across these calculated vectors in real time. To maintain high frame rates, the kinematic engine strictly separates the spatial path, the physical route the button takes, from time interpolation, which controls the velocity along that route. This split screen shows the mechanics in action. On the left, an EaseOutBack function graphs progress over time. On the right, a UI button traverses a curved parabolic path based on exact x and y coordinates at any fractional step. As the normalized time parameter t slides from 0 to 1, it drives the button's translation in sync. When the graph's peak overshoots, the button briefly scales past its normal boundary and snaps back, visualizing the getButton initial scale logic. Concurrently with that spatial translation, the engine must process color transitions in parallel. You cannot simply swap a background color mid-flight without destroying the illusion of fluidity. Instead, this requires a dedicated lerp color subroutine to blend the hues frame by frame. But attempting standard linear interpolation on a combined 32-bit ARGB hex value results in mathematical failure. The raw integer value of a color does not scale linearly. To fix this, we have to isolate the bits. This visual shows a 32-bit hex color code string being vertically sliced into 4 independent 8-bit computational channels: alpha, red, green, and blue. We extract these using bit.shift-right and bit.and operations. Once isolated, each channel value interpolates independently from start to end, driven purely by the time parameter t. Finally, the 4 values shift left and merge using bitwise OR operators, constructing the exact color for that single animation frame. Fluid UI motion is not an artistic output. It is the result of rigorous, high-frequency parametric calculus applied to independent view properties simultaneously. This underlying complexity creates a new architectural challenge: configuration management. A single component needs to support over 35 layout permutations and 30 easing types. The solution is exposing these internal variables as designer properties. In this split-screen graphic, you can see glowing lines routing raw configuration data from the B4X demo page interface directly into the Apply Designer Props code block, feeding the component's state machine. This means hot swapping an animation behavior, like switching the physical path from a parabola to a line, merely feeds a new routing parameter into the existing engine. The underlying logic remains completely intact. This modularity extends to the component's event dispatching architecture. A physical screen top on a nested, spatially translated button bubbles up to the main application. It registers as a single-line boom demo boom button click interface, passing only the exact index and tag payload. The illusion of organic fluidity in the UI is sustained by structural decoupling. The most robust custom components succeed not by complicating the main rendering thread, but by separating their z-index hierarchy, their coordinate mapping, and their mathematical interpolation engines.